Awesome. And then again, welcome. I'm Courtney Dean. I'm our program director here at Neuromatch. So it's really awesome to see all of our impact scholars here. And I know we opened this workshop up a little bit wider to our Slack community as well. So welcome to everyone that's joining us. I'm really excited to introduce Dr. David Edge. He is a assistant research professor at Northern Arizona University, and he will be here to present the seventh module, I believe, for the Leapfrog tutorials. So I will go ahead and pass the time over to him. Please use the chat for questions. There'll be a couple times throughout the presentation where we'll stop and check in on those questions. So feel free to use that chat function. But that's all I have. So I will go ahead and turn it over to you.
All right. Thank you, Courtney. And good morning. Good morning for me, at least. So yeah, this is a tutorial from the Leapfrogs program, which is an NSF-funded project. This is one of 7 parts of Leapfrogs, and I'll give you a link at the end of this presentation to find the others. But today we'll focus on packaging software for sharing. This should be a universal guide, but most of my examples today will be in Python or R. Just as the most common languages that we use for sharing, specifically research software. And I should say sharing research software in open source formats. So a lot of people still use MATLAB as well, but we're trying to encourage open source code. So the presentation today is broken into 3 parts, and the first part is the basics of software packaging. So what are software packages? So a quick definition, collections of code, data, and documentation bundled together in a standardized format. So different languages tend to have standardized formats that they publish software packages in. Code is probably the most familiar part of this to everyone. So we all write scripts for doing our research. And a software package is a more standardized way to distribute that code or those scripts. The general purpose is to distribute reproducible functionality or reusable functionality to others. And the structure is source code, metadata, documentation, and dependencies. So some examples of this, NumPy, the logo down here in the bottom corner, familiar Python package, pandas or matplotlib. And for R folks, dpdplyr, ggplot2, and Shiny are some common examples. What's inside of a package? So if we slice this thing open and take a look inside, we have the code, which includes things like functions, classes, and algorithms. If you're working more in Python, you're more used to object-oriented, so focusing on classes. And if you're more focused in R, you're generally thinking around functions. Documentation, so this is examples and instructions, the overall API reference, the metadata. So this includes information about the package. For R, this is called the description file. This is generally in a machine readable format, so the metadata can be pulled and used in resource locations. Tests, so verifications of functionality. We write tests, so when we change our code, we can make sure that our package still works as we expect. And build scripts. So this is a little deeper under the hood. This is instructions for installing and configuring our package. So why do we want to package software? So this is generally for an audience of researchers, and researchers write scripts generally to do our analysis. But why might we want to package our software? So first, reusability. You use your code across multiple projects. Packages are a really nice format for reusability. Generally, if you're writing in scripts, you have to repurpose your entire script. You have to do a lot of extra work to make that the pieces of that script reusable for the future. Sharing, distributing your work amongst colleagues and community members. So making your code usable across a wider network. This is specifically about the documentation. So how is this code used? So just making inline notes in your scripts. We can sometimes share code that way in a smaller network, but the wider you distribute it, the better your documentation needs to get, and the more modular your code will need to be. Reproducibility. So ensuring consistent environments for analysis. So if somebody takes this onto a different machine with a different operating system, a different version of the programming language, how do we ensure that they're getting the results desired, that the code's functioning the same way on their machine? Maintenance. Easier version control and updates. So as our code changes over time, it's much easier to work to maintain your code in a package format. Credibility. So if you're sharing this, you want to make your work used across the community. Presenting it as a package lends credibility, and this credibility is not unearned. There's extra work involved in making it a package, but for all the reasons listed above, your package has more credibility than a script alone would. So how do we decide if it's time to turn our scripts and code that we've been using into a package? Does this code solve a general problem? So is this more than just a one-off analysis? Have we created some code that could be widely useful and used in the future by others? Well, I reuse this code across multiple projects. So the sort of activation energy required to spin this up as a package instead of just a few scripts. Generally, this is how some of my scripts have become packages, as I've used them multiple times across projects, and it's made sense to develop them into packages before thinking about distributing to the wider community. So will I reuse them myself? Will my wider lab group or colleagues start to reuse them? Sort of an organic way that packages develop. Would others benefit from this functionality? Kind of tying together I was just mentioning there. Is maintaining a package worth the overhead? So yeah, I mentioned there is some extra work involved. You'll have to maintain your package as the dependencies of your package evolve over time. Consider if it's worth the extra work of maintaining this package. And maybe you need a partner in that project. Maybe it's worth having a colleague that is already using the code that you can have to assist you over time. Can I commit to supporting the package over time? So can I commit my time? Can somebody else commit their time? Is it worth this extra time? And is it something that I can see in the future that I'm going to have time to continue working on? All right, so package dependencies. So your package is going to depend on other software that is being created by others. And there are a few things to take into consideration there. So generally, we want to prioritize modularity. So Python specifically calls individual Python files within a package modules. And the idea here is to separate your code into little bundles that kind of work semi-independently of one another. So a package can have multiple modules that are loosely coupled. And generally, their dependencies may have some overlap, but an individual module will share dependencies in common. You want to use optional dependencies to the degree that that's possible and keep your core dependencies minimal. So the dependencies they're truly required to make your software work. We want to minimize that as much as possible. And where possible, we'll have optional dependencies that allow additional functionality that's not necessarily core to the main use of our software. We should use tools that resolve and check for conflicts. So there are some ways that we'll talk about that we can do this automated. So there's a package for Python called Hatch, or the software pip for Python. And also a more general use case, GitHub Actions can check for conflicts for us. And this works language independent. So another consideration after thinking about dependencies is API design. So your application programming interface, if you aren't familiar with that acronym. So our API design, there's a lot of facets to API design. So the way that people interact with your software, your application programming interface, includes all of these different facets. So naming conventions. So how are we going to name our functions and classes? We should have a standard naming convention that we're going to start with and keep. Stability. How does our software change as our dependencies change? Avoiding global state. So we want to focus on the environment we're intending to work in without creating global variables. Hints. So as you start to access the functionality within your software, you can, in RStudio, for instance, as you start to fill in arguments to functions, you can have hints appear. And this has to do with the way that we form our documentation, but we want to keep that standardized. How do you handle errors? How deep do you want to go in anticipating the different types of inputs that users will put into your API and how you handle potential errors? Generally, there must be some level of uncaught errors that we let the programming language deal with. How deep do you want to go in handling misuse of your functions or your classes by users? Backwards compatibility. So we need to think about future development when we're thinking about how we're writing our code. Performance. So how deep do we want to go in terms of optimizing performance? So it's much less work to make your functions simply do the job that they're intended to do, and generally more work to make them perform optimally. So how far do we want to go in that direction? And scalability, you might think of as a piece of performance. So we can make our functions in R, for example, scalable by making them pieces of one another. And then lastly, testing. So we'll talk a fair bit about testing today and how that's set up and how that's automated. We can generally write our code from a testing-centered framework. And tests will be an integral part of developing the code. Software repositories and registries. So this is where your software will be distributed from, where it's generally stored for public availability. Quick definition. This is the centralized storage and distribution platform for packages. So pip that I mentioned before is an example for Python. CRAN would be the most common example for R. So this offers hosting, versioning, documentation, and discovery. So this is where your package will be available, where archived versions will also be available. Documentation of your package can also be available here. This may not be the main source of documentation, but documentation in some form is likely to exist alongside the software in the registry. And this is also an opportunity for discovery. How will people find your package? Public versus private. So the registries I've mentioned so far have been public registries, but private, so organization specific. So perhaps at your university or within your sort of lab group, you might have a private package repository. Types of registries. I've also mostly been talking about language specific, but if you have a lab group registry or a organization registry, you might have something that is more general purpose, such as a registry on GitHub that offers a registry across languages. So some major package repositories for Python, generally PyPy and Conda are the most used package repositories. And for R, we have CRAN and Bioconductor. Bioconductor is more specifically for the biological sciences. CRAN is very broad-based. A lot of packages on CRAN. And then cross languages, I mentioned GitHub offers package registry as well. This is a bit less formal. There are generally not as many requirements to follow to get your package suited to GitHub, as opposed to something like CRAN that is a little more curated. GitLab similarly. GitLab is a similar cousin to GitHub, also offers package registry that is language independent. Package managers. So package managers are tools that interact with repositories. So package managers, they facilitate installation, updates, and dependency resolution. So when you are trying to recreate an environment that supports the running of someone else's script, you might have an environment file with a list of packages and hopefully their versions. And this allows you to recreate that environment. So you can install all of those packages. Hopefully, if the versions are pinned, you don't have to do any dependency resolution. But perhaps you're working with a different version of Python, for example, and you may have to resolve some dependency differences when you change language versions, for example. Examples of package managers are pip and conda for Python. R generally does this within the language itself. So install packages. This is a basic functionality of R, kind of built into the language itself rather than as an additional package. More universal, we have Homebrew, apt, and yum that you might be more familiar with if you're used to working from the command line. All right, getting started with package structure. So we've talked about different facets of packages and the infrastructure that supports them. So the package structure itself, the figure over here on the right is specific to Python packages. So we'll start there. And so everything in that structure falls within a package directory. So it's called my package up there. In the bulleted section, I'm calling it my underscore package. This is the name of our package directory. Underneath that, we have generally a setup.py file that walks through sort of the setup of the package. This is the deeper under the hood stuff. Setup.py is generally not written by the user, but written by a Python package like setup tools. Within our package, we also have modules. So this would be the actual Python code. These are Python files that you might be more familiar with writing if you hadn't written a package before. So we might think of these as our scripts where we bring in the dependencies at the top of our scripts. And then we have some algorithms that develop our software functionality below that. We'll have tests within our Python package. We'll talk a little more about tests and different types of tests a little later. But tests basically check the functionality of your package, make sure everything's working as you intend it to work. And then we also have a README file. And a README is just a high-level explanation of your package, the intended functionality, a little bit of install instructions, and then some basic examples. Our packages follow much of the same structure. So the description file is the sort of metadata for your package. The writing of the description file for R is automated. The R directory is where you put your what Python generally calls modules, but these are R files with all of your functions and classes. Man is another automated directory. This is created for all of your API documentation. So there's a specific package in R for creating that API documentation that also creates this man directory. And again, we have a test directory and a README file. So a lot of overlap between the overall basic structure here, but there's some subtle differences between the two. So documentation best practices. So an important part of putting together a package is good documentation. It makes it easy for new users to pick up and use your software. So README is sort of the high level version of this. This is the piece of your documentation that you are authoring yourself. It's not generally an automated piece of the documentation. And this is the broad overview. You want documentation of your functions and classes. And generally this can be automated. There are options for this in both R and Python. Some tutorials. So you might have Jupyter notebooks for Python or vignettes for R that offer example use cases. Your API reference, so how you interact with functions and classes. And examples. So examples don't necessarily have to be at tutorial length. Examples can be just how you use an individual function. So an example of how to use it, perhaps with some data included as well. So as I mentioned, there's some tools to do this. So Python offers a package called Sphinx or Read the Docs. And R offers packages roxygen2 and package down. roxygen2 is how we get sort of our API reference and our function and class documents. And package down is how we build a sort of website reference. So how do we put it all together in a readable format in HTML to share more widely? So testing, I mentioned a couple of times that we're going to write tests for our package to make sure that the functionality is doing what we intend and expect. And there are different classes of tests. So at the bottom of this pyramid here, we see unit tests. These are the most basic tests, sorry. So in testing a simple individual function, we're performing a unit test. The test of our math function, we can put in a simple math function that does square roots, and our square root of 4 should equal 2. And we can write a test that says very explicitly the outcome of square root 4 should be 2, and that would be a test of our square root function. Getting up to integration, we might want to integrate multiple functions. So we might want to integrate our square root function with a graphing function where we take the square root of x and we have a graph that plots the square root of x for all numbers across the number line and produces a graph. And we can integrate the specific graphing function with our square root function, and putting those together is integration. So the output of one function going into the input of another function. And then end-to-end is a test of sort of a full potential workflow. So this could be something like our vignette in R would be an example of an end-to-end test, where we test a full workflow with a good example input data. We run it through multiple of our packages functions, and we have some expected outputs across that tutorial or vignette. There are different frameworks for testing and different packages or libraries that offer unit tests particularly. Generally, we incorporate these in our package. This is best practice. Package versioning. So the most popular and common way to version packages is semantic versioning. So you might have seen this framework before with major, minor, and patch versions. So perhaps the very first version of a software package you're releasing is 0.0.0. With changes to that package across these different facets. So a patch where you're fixing a bug, you would increment the last number. A minor patch where you're introducing some new functionality, you might increment that middle number. And a major change where you are sort of breaking previous versions. So you're losing backward compatibility. Because you're making such a significant change to your software package would be a major change. We generally include release notes explaining what's happened. And generally the release notes, the complexity and detail of release notes increases going from right to left here. So if it's just a simple bug fix, the release notes may be pretty short. If you're introducing major changes, pretty significant lengthy release notes would be required. Generally, versioning is incorporated in Git. Git is the major pathway for versioning, or the major software used to implement versioning. Versions are implemented with tags. So Git tag is a command within Git where you introduce your version. We also use branches. So our stable version of our software generally lives in our master branch. And we might have another branch that we call dev or development, where we're making changes actively to our software, but it's not considered fully tested and ready for public consumption yet. Publishing your package. So first, obviously, we need to build our package. We need to create all those different directories and files that we looked at before. But once we have that full structure complete, we can register, set up credentials on GitHub or PyPI, for example. And then lastly, uploading our package. So pushing it to GitHub or uploading it to PyPI. For Python, this is the dist directory, the distribution directory. And it may be a little bit more involved. So for something like CRAN, there's a review process. A lot of that process is automated, and you can test some of this yourself with a DevTools package for R. But it varies by registry that you plan to use. Package maintenance and resources. So your maintenance of your package over time. So you'll have version updates, issue tracking, and documentation alignment. So in GitHub, for example, you'll post version updates. Those version updates will include changes to your documentation. You'll have issues that come up over time. Those issues could be resolved by pull requests. You might have a broader community discussion. If you're unfamiliar with these aspects of GitHub, GitHub is generally the venue for open source software development. So getting familiar with these tools and how they work in GitHub. Issues are generally where we raise bugs for software. Discussions are often where we talk about sort of higher level things for software, sort of the direction that the software package is going, or future development angles. And pull requests is generally how we resolve these things. So issues might be resolved by a pull request where a user goes in and fixes a specific bug that they've found in the software and offers a patch for the software. There are also ways to do this specifically for R and Python, but GitHub is how we do this sort of in development, and it's generally possible to keep your GitHub version, your latest development version, or sorry, your latest version that's ready for public consumption, up to date with your published version of your Python or R packages. So this is the end of the first section where we go over sort of the broad brush, what is in a package. So I'll stop for a minute and ask if there's any questions sort of on this first section of just, what's a package, what's in a package. Yeah.
Yeah, we didn't have any in the chat yet, but for folks here, feel free to use the chat, or you can also come off mute and ask your question directly.
Okay. Well, I'll move on to section 2 then, if there aren't any questions pressing right now. And I'll save a little time at the very end for questions as well. So this second section here is on documentation and testing. So how do we build robust and user-friendly packages? All right, so why does documentation matter? Documentation matters for knowledge transfer and adoption. So we want to enable new users to pick up and use your code. Um, and generally, new users adopt code that is relatively easy to figure out how to use. Um, so you need to either have code that is offering very important functionality that users are willing to put in the work to learn how to use, um, or if your code is maybe less unique or more niche, you'll need to facilitate their adoption with better documentation. Maintenance. So in general, it can be a while between when we go and maintain our code. We get busy, the semester picks up, and there's a lot to do, and we're scrambling in that last week of the semester, this week or next week, to go in and make bug fixes, maintain your package. And it's been a while since you've maybe looked at that code last. So future you will thank past you for good documentation. Good documentation generally means fewer support requests. So I mentioned pull requests in GitHub are ways that users can offer patches, and it's much easier for users to go in and figure out how to fix a bug themselves if they have good documentation to follow. Good documentation is also a quality signal. So it's a quality signal because it truly signals that you've done the work. So if you've created good documentation, it suggests that you've put some good thought into how the software works and how users are using the software. So it's not just it's not a false signal. It's a signal that you've gone in and done the work. Documentation pyramid. So there's a sort of hierarchy here in how documentation builds on itself. So starting with your API reference, in R, this is how we document individual functions. So we write with R oxygen 2 notation, sort of what the possible arguments to a function are, what types of inputs each of those arguments may take, and also an example of how to use this function. And putting this together, this becomes our API reference. So it details the total use of that function. Next level up are tutorials. So these are task-oriented guides. So generally good and common use cases for how to put some of our functions together. This is generally how we learn how to use a new package. Quick start guide. So this is sort of the very basics of how to use your package. So this may involve using sort of the very base functionality with some examples. And then lastly, the README or overview explains in sort of broad brushstrokes what the package is for, what the main goals of this package are. So that kind of rounds out the documentation. All these things sort of work synergistically together. And much of this, or all of this really, should be published in one place. And there are ways to do this in an automated way. With R, this is a package called Package Down that creates a website from all of this documentation in an automated way. Documentation best practices. Be consistent. choose one style and stick to it. So your documentation should follow a similar format throughout. Automate. Use tools to generate docs from code. So I just mentioned package down and roxygen2 for R. There are similar tools that I mentioned already for Python as well. Examples include practical code snippets. So these are very short, to the point examples that show the functionality of individual functions. Keep your documentation updated. So as we make changes to our code, we need to make changes to our documentation. Audience awareness. So don't make your examples too technical or too specific. Try to create examples that can be broadly applicable to the audience, as wide as is reasonably fit. Progressive disclosure. So use simple concepts first and then add details as you go. And then lastly, test your docs. So we can implement tests within GitHub, for example, that actually build our documentation to make sure all of these examples that we're using actually work. So this is a way to ensure that as we change our code, as we make new versions of our packages, that all of our examples still work. So it's a good idea to build tutorials or vignettes within your package to ensure that you're not making breaking changes to your code as you go, or just to see what updates you need to make to your documentation. A README file. So a README file is ubiquitous across software. This is not specific to R and Python packages. Generally, software contains a README file that provides some basics about the package. So package name and logo is generally included in a README file. So you might have seen this on GitHub, a package name and logo generally at the top of a README file. A concise description. So this is generally pretty brief, a 2 to 3 sentence description of kind of what the package exists for. Installation instructions. So this might be a code snippet, a simple pathway to get the code working on your machine. So you'll need to consider that this is independent of operating system, as well as include instructions for specific language version if that's necessary. And then next, we generally have a quick start example. So what is the most common starting point for people walking into your new package as new users? So perhaps we might have a loading data example. So this is a common example for how to get started with a package. How do we bring data into Python or R in the format needed to work with our package? And then there are lots of other aspects to a README here that we might want to include. Those top 4 are kind of the most common and most important. But there are a number of other things you'll want to include for a full and complete README file. I do list license and citation on here. Those are often separate files. There are license and citation files that we include. And GitHub now has the capacity to machine read license and citation information, making it easier to cite packages and reuse packages. So generally best practice that those are now separate files. So a little more on the quick start guide. So what should this look like? We should have installation instructions. So What does package installation look like? Like I said, are there any specifics about operating system or language version that a user might need? A minimal working example. So an example of how to use a basic function of the package. Some core concepts, so we can describe some basic uses of the package and maybe include what the basic functions or classes that involve those core concepts. Some common use cases. So we might describe common use cases and perhaps link to some of our tutorials. And then lastly, troubleshooting. What are some common misuses or misconceptions about the package that users generally run into? So if you have the opportunity to sort of test your package with some students in your lab group, get some examples of problems users generally run into off the bat and head those off. And then publishing. So we can link to package documentation. So if your package is on GitHub, you can have a link to the website where your documentation lives. And ideally, your documentation publishes via GitHub pages, through package down or some other automated system to get your documentation linked directly from your GitHub page. Tutorials. So these are more in-depth examples. So we want to show some high-value use cases. We want to walk through examples that users will find interesting. We want to showcase the value of this software package. Why would users want to take the time to learn how to use this and pick this up? So if you've spent time producing nice plots in your software package, we want to show these pretty plots to the users. Or if we've spent a lot of time, coding up an algorithm that's been in the literature for a long time, we want to showcase the use of that algorithm and the outputs, and showcase, how to get from input data all the way to those end results that we've spent a lot of time developing. It's nice if tutorials can be interactive. So Jupyter Notebooks provides a good example of this. Offers the ability to publish interactive tutorials, such as through Binder on the web. There's an option to do this with R as well, with MyBinder. Generally with R, we don't use interactive notebooks. We publish vignettes in PDF format, but there are options for interactive tutorials. Lastly, we want to make sure our tutorials are reproducible. So perhaps the clearest way to do this is to make the building of your tutorial part of your continuous integration workflow. If you're using GitHub, for example, you can use GitHub Actions to do this. But we want to make sure that we're reproducible across operating systems, across language versions, and we can test this in a testing matrix that we'll go over here. The API reference. So the API reference is generally the longest, most comprehensive piece of documentation because it goes through all of your modules and packages, modules and sub packages, all of your classes and your functions, and describes sort of the structure of all of this, as well as the inputs. It gives all of the important technical details of how the various aspects of your functions and classes work, how they're interrelated, any data or global variables that are contained within your package, cross references. So how different functions may interact with one another. All of this is contained in your API reference. Your API reference should generally be generated automatically. This is done with doc strings and R-Oxygen2 I've mentioned before. For R is generally how we do this. And there's a similar functionality for Python that offers automatic generation of API references. Generally, as you're going through and writing your modules or your functions, in R's case, it's a good idea to write documentation as you're writing these functions and modules. Writing them as you go, you'll be keeping top of mind exactly how all of these functions and classes work. And be writing examples. And at the end, what you'll have is the ability to automatically generate all of this reference documentation, so long as you've been writing those doc strings as you go. So here's an example. So this is API documentation from NumPy. So you can see here at the top, we've selected API reference. And we're looking at how to use an n-dimensional array within NumPy. So this documentation is largely automatically generated. So you can see there's lots of individual calls for n-dimensional array. And how to use each one of these is included in this API documentation. So this is a very large document because there's lots of different potential use cases. And this should generally be generated automatically with some writing of text merely to sort of introduce the concepts. So for Python, the doc string looks something like this, with a sort of description of the function, the parameters of the function. So there's an argument, there's the type of input that you're giving, and then there's a description of that input. And then you'll also describe the return values. So the type here is a Boolean, and then you provide some description of that return value. This looks very similar to the doc string for R. Just the formats are the main differences here, given that we're looking at a function for Python. Next, testing. So why testing matters? So we want to verify that the code works as intended. So does the code actually do what you want it to be doing? We want to catch breaking changes as they occur. So if we have a test to make sure that our specific function works, when we go through and make changes, suppose we're trying to fix an existing bug, we don't introduce some new problem. We don't break the code by doing that. Refactoring confidence. So refactoring, generally, we're changing the way that the code works. We can make changes to our code with less concern about breaking things if we have good tests. Our design quality is better when we have good tests. So generally, testable code is better code because we've considered and thought about how the code works and how different modules interact with one another. Documentation. So tests offer examples of how to use the code. So this can be included in our automatic documentation, our examples for users. collaboration. So it's easier for others to contribute with better tests. And lastly, peace of mind. Just having all these tests just generally makes your code easier to work with, and it makes it it makes you more confident that you're not breaking things when you go to make changes. So testing pyramid, I've shown this before. Just adding some arrows on the sides here. So I explained before that unit tests are sort of the fundamental building block of tests. And generally we have a lot more unit tests and they are a lot faster to run. And then as we work our way up the pyramid here, integration tests, there are fewer integration tests than unit tests, and they're a little slower to run because they integrate multiple functions or multiple parts. And then these end-to-end tests are generally the slowest things. So if we're building a full tutorial or vignette, these are going to be generally slow to run. And we generally don't need too many of these because they're testing much of the functionality of our software. What a unit test looks like. So these are single functions, methods, or classes tested in a isolated, very simplistic way. So we're testing the very basic functionality here. We want to make sure that we're getting the expected behavior. So you see equals equals here, meaning is this true? Is one side equal the other side? So this is a test for expected behavior. And then this offers failure and debugging opportunities. So you can see that this test failed, and we see exactly how it fails, where the problem is. It's very simple to go back in and look at what's performing in a way that we did not expect and why. So this allows for very easy bug fixes. Test-driven development. So I mentioned before that it's possible to write your software basically around your tests. So the process for this looks something like this. So you can write a failing test for a new feature. So this test fails because the feature does not yet exist, essentially. Run the test to confirm that it fails. And then you can implement the new code centered around the test. So making sure that you implement the code in a way that this new test will pass. Run the test to confirm it passes. And then refactor the code, keeping the passing tests. So this is reorganization of your code around this new functionality. So this offers some benefits, including focused development. So you're kind of choosing this new feature based on this test outcome. Better test coverage because you're starting with the test. So you're always going to make sure that your new features are being tested. You have clear requirements. So you're setting it up at the beginning to have this functionality that's very specific. And your designs will generally be simpler. So it's easier to make your code modular and easier to read this way. Notebook-based tests. So this is sort of at the other end of the pyramid. So we can use a notebook tutorial as a test. We can, so we'll write our, Jupyter notebook or our markdown document, our vignette, and have that document be built within a GitHub action. And then we can compare our newly rendered notebook that was built by GitHub Actions to our previously built notebook. And we can see if these two notebooks are the same. So this is a way to validate that nothing in your code has changed. If you can build this notebook in the same way This is a way to test that no piece of functionality has changed that's important to this particular tutorial. So this is a pretty straightforward and useful way to test your code. That's pretty readily utilized. So long as you have tutorials that you are providing with your package, you have an opportunity to do notebook-based tests. Test coverage. So test coverage, you can automate basically the percentage of your code that's covered by tests. And you can offer this included with a sort of GitHub badge that shows what percentage of your code is covered by tests. So if you are going about this kind of trying to initiate tests, this offers you sort of gamification to get started with testing and build out how much of your package is covered by tests. It's also sort of another way to show that your code is reliable and credible. So if you're including a badge in your GitHub release of your code, you can show that a high percentage of your code is covered by tests, and this reassures users that they're getting a serious and credible software package. So here's some additional resources for going through and looking at testing and documentation. And this is the end of the second part of this presentation. So I'll take a minute here and allow a second for questions if anybody wants to break in.
I sort of have a question, or maybe just a comment to see if I understand things correctly. So in terms of packaging our work for research, it seems to me that mostly the use case would be for methods, like if we plan to reuse a method or a particular methodological approach, that's the thing that could be reused, and not just by us in the future, but by others, and that would be the main purpose of creating a package from our work.
Yeah, that's generally how I would understand it as well, is reusing methods. I'm trying to take your concept generally because I don't know what field you're speaking from. But yeah, I think that's generally the correct take on this. If the more specific your software is, the more specific your scripts are, the less reusable that they're likely to be. And the more generalizable your methods are. And so speaking from a methods section of a paper, yeah, I think that's a pretty reasonable take on packaging, is that your packaging methods.
Okay, yeah, thank you for that confirmation. Yeah, I come a bit from a neuroscience background, but
Okay.
I guess I do more research questions, and I'm dipping more into methodology and programming now. So thank you for answering the question.
Yeah, thank you.
At first, thank you for your complete presentation. And though I have a experience in coding, I'm completely new to software packaging. So maybe my question is a bit basic, but how should we decide to represent our code scripts as a package? For example, I have a project and consists of some Google Colab notebooks, and each notebooks has its own, for example, test for its functions and classes. So how should I decide to integrate them as to represent a package, for example?
Yeah, so let me clarify. Are you asking maybe how many of these notebooks should realistically be packaged together.
Yeah.
So sort of, yes?
Yes, yes.
Okay. Yeah. So there's certainly different angles on this and different sort of breadths represented by different packages. So how niche or how broad you want your individual package to be maybe depends on the user group that you're targeting. So if you're targeting a kind of specific scientific domain, for example, in the dendrochronology community, the group that studies science of tree rings, there's a package for all of dendrochronology that tries to include methods. So as disparate from just actually dating trees all the way down to sort of climate comparisons against their tree ring data. So they've sort of tried to target a whole scientific domain with that package. There are, much more specific packages that target kind of fairly narrow functionality. So looking at maybe the spectral character of a time series, for instance, and this might be, very narrowly focused on Fourier transform because someone has taken the time to look at 5 different algorithms for Fourier transform, and they're trying to really get the computational time down to a minimum because they're looking at very long time series, and it might be very, very niche, but they've also kind of dived very deeply into the subject area. So I'd say that there's a lot of room for kind of thinking about how broad versus how narrow. But generally, it's thinking about what audience you're targeting, and are they likely to pick up and use many of the pieces of this package, or does it make more sense to have it be a little more modular and have them, more specifically targeting different user groups? So maybe that's not super satisfying. It depends is the answer. But yeah, I'd say there's a lot of room for difference there.
Thanks a lot.
Yeah. All right, if there's nothing else, I'll skip on to our last section here. So this last bit is about continuous integration and publishing. So how do we automate our updates, our testing, and our sharing? What is continuous integration? So you might have heard this term before, but if you haven't done a lot of software development, you may not be able to specifically define continuous integration. This is the automated process of integrating code changes frequently. So if you are currently or have started using GitHub for software development, this is the most common place to do that. The key benefits are you can automate your testing. So all of those tests will be run sort of each time you push changes. You can have consistent build environments. So you can sort of test different environments to build your package in. You have reduced manual intervention. So there's less need to go in and fix things so long as you're continuously integrating. And generally, this improves code quality because you'll have updates each time you try to push changes related to these different tests that you've triggered automatically. So I mentioned GitHub. GitHub Actions is where a lot of this will take place. So GitHub has built-in options for continuous integration and delivery. So that CD is continuous delivery. Generally, these two things go together. So in GitHub, these automations are event-driven. So most commonly, what would happen is you make changes on your local computer. You commit those changes, so basically saving your place, saving your changes, and then you're pushing these changes. So pushing as in updating the version of code that's stored on GitHub. And this push event, where GitHub receives this change to your software, initiates an automated workflow. So these automated workflows can do a lot of different things. You can write them yourself to do very specific things, and you can pull existing workflows from the very broad GitHub marketplace to do various things. An example workflow might look like this for your Python package. So at the top here, we're telling GitHub Actions what the trigger is. So your push event to a specific branch, the main branch, or a pull request to the main branch. So either of these will trigger this workflow. And then down here, the jobs within that workflow. So we're going to run on this specific operating system, the latest version of Ubuntu. And then we're going to use a predefined action. So this checkout just means that we're pulling the latest version of your repository that's just been updated through a push or a pull request up here. We're going to set up Python and run on version 3.10. And then we're just going to install our dependencies. So this is a generalized install dependencies. It's run with this very specific script to run Python on Ubuntu. Pip install your dependencies. And then lastly, we're going to run our tests. We're going to use PyTest to run all the tests in our package. So this is a pretty standard example workflow that you might use for a Python package that would automate installing your dependencies and running all the tests for your package every time you push changes or initiate a pull request. A step further would be matrix testing. So you can automate this as well, and you can test, you can run that workflow we just showed across multiple environments. So we can run it across multiple Python versions, across multiple operating systems, and across multiple sets of dependencies. So this is a way to ensure that your software package works in lots of different user systems, and we can keep track of sort of what Python versions we're compatible with, what operating systems we're compatible with, and what sets of dependencies are required. We can also implement continuous integration for our documentation. So we can build all of our documentation. We can test our examples. So we can run all the examples that we've included in our package and test that they work. We can check for broken links. We can do this in an automated way. And then lastly, we can publish all of our documentation via GitHub Pages. So GitHub Pages offers free hosting of static web pages. And there are packages like Read the Docs that allow us to publish all the documentation for our package via GitHub. And all this has become very standardized. So long as you're following the right format in developing your package, you can create a pretty useful and nice looking website related to your package in a pretty standardized automated way. So you can find lots of help on the web as to how to produce a website related to your package through these avenues. We can build our packages using continuous integration. So we can ensure consistent build environments. We can test the actual package. So we can build the package, we can put it all together and test the actual package as it will be published. And then lastly, we can verify that the metadata is correct. So something like this little snippet below, we can do all of this within our GitHub workflow. All of this can be automated. We can publish from GitHub, so we can share our package from GitHub. So we can use git tag to automate new releases with associated tags. So this allows for automatically changing our version number each time that we introduce a new version tag with Git. We can synchronize the GitHub and repository versioning so that we can have the same version distributed in both places. And this is all enabled through GitHub Actions, which include secrets. These secrets allow for interaction between GitHub and our repository, as well as various other links that you might want to make between GitHub and external resources. So secrets are basically passwords that you provide to GitHub Actions to allow GitHub to interact with external resources like a repository for Python or R. You might also want to interact with some other external registry. Docker, for example, you can use secrets to push a container that you've built in GitHub to a Docker hub. There are many other examples of places that you might want to introduce secrets, but this is a convenient way to keep your GitHub version of your package aligned with other sources. Publishing triggers. So how do you automatically publish your package and when do you want that to be updated? So you can make this manual. You can trigger GitHub Actions manually only when you tell it to. And this is useful for sort of one-off releases, small changes you've made, or if you want to just update your website on a less regular basis and have kind of full manual control over what that looks like. Probably a more standard way to do this is tag-based publishing. So every time you use a new tag, this is a version that you're giving your package. And your continuous integration workflow watches for these push events with tags. So if you're using semantic versioning, like this example here, your specific package version is associated with a specific tag, which is also associated with a specific release and DOI of your package, which is also released as a new GitHub Pages webpage. So all of these things are simultaneously released. They're all integrated, they're all tied together. So a good checklist here that you might want to institute for your package. Here are some things that you can and ideally should automate. So putting all of your tests in here together in your package. So every time we push or pull request on our package, we run our tests. Also, we want to build our package. So putting together all the package setup and actually building out the package and putting this together and testing it. We want to generate all of our documentation. So all of those API documentations, all of our package tutorials and vignettes, we can generate all of this each time we push or pull. Our releases, so this is a word that GitHub uses. The release is your specific version, which is associated with that Git tag, or the version of your software. All of these can kind of be used interchangeably. They just occur in sort of different places, but they're all interrelated. And then your dependencies, so keeping up to date, you can use bots to check all of your dependencies, make sure that there are no security vulnerabilities with any dependencies, for instance, or changes in your dependencies that you may need to check against. So you can make all of this sort of hands-off and run all of this in an automated way. All of this can happen each time you push or pull against that GitHub repository. So here are some additional resources. So I mentioned that you can find a lot of this on the web. There's a lot of great documentation on GitHub Actions for packaging, and here are some examples. I mentioned that this is part of LeapFrogs. So this is one of 7 modules within LeapFrogs. These here are Python and R specific. So a lot of this is sort of language independent, but we've made separate platforms for Python and R here. And that's the end of this presentation. So we have a few minutes here for questions.
Awesome, thank you. We do have one in the chat, so I'll go ahead and start with that one. So first, this is from Ignatius. So enjoyed this lecture, and then as I continue learning to code, how can I plan efficiently to minimize cloud resource consumption? Specifically, how can I avoid rerunning the entire code from the first line every time? How can I use this concept of packages to help with this? And for context, this was when you were talking about testing, I believe. But
Yeah. So your interest in sort of minimizing cloud resources. So GitHub Actions offers quite a lot of computational resource for free with standard public GitHub repositories. So generally, with package construction and all of this sort of automation included in continuous integration, it's unlikely that you're going to run up against cloud limits for your package. So you can run something like 200 hours a month for free on GitHub Actions. So all of your automated tests should be relatively simple and modular, just using basic functions of your software. You can minimize a little bit how much of your tutorials are run each time. So if you have kind of complex tutorials, say you're running a model and you have many iterations of that model that you're testing to get your uncertainties, and you might just reduce your ensemble number for testing, and explain in your vignette that you're using a reduced number of ensemble runs to reduce sort of just your resource consumption for testing your package. There are a number of common and straightforward ways to do that for package testing. It's also possible to set up your GitHub Actions so that your tutorials are not running each time and you're only running your unit tests. Unit tests can often be sufficient for your continuous integration, but it's unlikely in general that you're going to run up against limits in GitHub Actions with 200 hours a month per package.
Awesome. I don't think we have any other questions unless someone else has one. Great. Awesome. Well, thank you so much, Dr. Ed, for being here and sharing this with our scholars and our broader community. We really appreciate it. And for those of you that are here, we will get this posted so that we can share the recording with you. And Viviana will reach out for all of our impact scholars with the recording. So yes, thank you so much.
All right. Thank you all.
Thank you.